Well, greetings from the United States and from Chicago specifically. It's great to be talking with you today. Sorry that I can't be there live. As Jeff has probably explained to you, I've got a slightly pressing appointment this afternoon, but I'm looking forward to the discussion afterwards and to talking one-on-one about some of the things that are raised in my talk. So the title of the talk and the title of the book that I published in 2017, Beauty's Rigor, speaks to this idea that occasionally we run into works of design, architecture, industrial design, engineering, whatever, where the logic is kind of so distilled, so cleaned up, so clear that what we see is this kind of presentation of like physical principles. And that can be so direct, so the theory goes, that we find it particularly compelling and particularly beautiful. The rigor of beauty is the quest is a line from a William Carlos Williams poem, Patterson, and Williams' idea with this book-length poem was that you could find beauty in the kind of everyday. And certainly what I want to show in the work of this Italian engineer, Pier Luigi Nervi, is that taking seriously the kind of everyday considerations of architecture, structure, construction, taking those seriously enough can distill them all down into works of what we think of today as genuine art. So to begin with, Pier Luigi Nervi was an Italian engineer, born in 1891 in the town of Ancona. His father was a postmaster, which was a kind of upper middle class job at the time. And so Nervi moved around quite a bit, but ended up going to school in a Piarist school. Piarism is a particular sect of Catholicism that believes both in a very kind of sort of rigorous approach to learning, but also in a very particular type of social justice. So Nervi went to school not only with kids of his own stature, but from all across the kind of socioeconomic spectrum in Italy. And he blossomed into someone who I think is generally acknowledged as one of the great engineers, one of the great designers of the 20th century, and how he got there and how he came to do these building structures that are both incredibly impressive, long spans, some of the largest reinforced concrete domes ever built at the time, still some of the largest reinforced concrete domes in existence today, combined with this incredibly kind of delicate, graceful sensibility, how those large spans are rendered in these very, very finely scaled patterns and sort of rhythms, structural rhythms, and as I'll show, constructional rhythms. This, I think, is what made Nervi unique, that his spans aren't just kind of the biggest spans in the world, they're also some of the most beautiful. And to sort of set this up, I want to contrast one of the buildings that I'll look at on the right, the Palazzetto dello Sport, which he did for the Rome Olympics, which were held in 1960. At the time, like I said, the largest reinforced concrete dome in the world. It was beaten by another one that he did for the 1960 Olympics, and then for a long time, the largest reinforced concrete dome in the world, the one that beat both of these, was the King Dome in Seattle, where the Mariners used to play. And here I think is a really interesting contrast, because the King Dome should be something that we regard as even more impressive than Nervi's domes, because it's so much larger. But in fact, the King Dome was hated so much and proved to be such a kind of dog of a building that was actually imploded. It was blown up about 20 years ago, replaced with an outdoor baseball stadium. So why is that? Why do we feel this incredible affection for the structure on the right, beloved by architects, engineers, preservationists now, thank goodness? And why is it that the structure on the left we regard as, in a way, kind of disposable, right? Lived its day in less than 25 years, while the structure on the right seems rather timeless. And the answer to why Nervi was able to do this in a way that other engineers weren't, I think goes to his, or speaks to his background, and to the way that he ran the two offices that he ran throughout his career. Nervi was a structural engineer, sort of white-collar profession. He had an office and an apartment on the Lungo Tevere in Rome, just north of the Piazza del Popolo. You see that on the left. It was a design-build project. His office was in the ground floor, and the Nervi family had the apartment, the penthouse apartment, on the roof. That was his sort of white-collar profession. In the mornings, he worked there. And then in the afternoons, he would go down to Maliana in the south of Rome, where he had a construction business, Cantieri Nervi e Bartoli, where he was able to experiment firsthand with these very kind of in some ways primitive, in other ways very advanced methods of concrete construction. So a white-collar profession in the morning, a kind of blue-collar entrepreneurial business in the afternoon, where he would get his hands dirty and be able to test out the theories that he had sort of been calculating in the morning. And on the right, this is a warehouse that was built out of prefabricated ferrocemento panels. I'll talk about what ferrocemento is here in a little bit. But important, I think, just to know that he had these two businesses that he was running. Very often, Nervi e Bartoli would build the designs that were that came out of the office on the Lungo Tevere. They were kind of synergetic in that way, but they're two very, very different kind of aspects of the profession. And this twofold approach really came from his education. He was a brilliant civil engineering student at the Università di Bologna, where he had these two very influential professors. Silvio Canavazzi on the left was a theorist, one of the first engineering academics to come up with ways of calculating so-called hyperstatic structures, reinforced concrete structures where there are so many load paths that it's kind of impossible without using statistics to know really where the loads are flowing. And Canavazzi theorized about how those might be traced. Kind of white-collar, academic, chalkboard engineer. On the right, Attilio Muggia was a professor of construction, a professor of how to make formwork, how to build out of concrete, how to run a construction job successfully. And Nervi learned from both professors. Muggia was what today we would call an adjunct. He had a firm that it was his sort of full-time job, and then he would come in and teach a couple of classes a week. And Nervi ended up going to work for him in Florence, and in particular in Prato, the town outside of Florence known for its fabric industry. These are early buildings that Nervi superintended for Muggia after he left school. And you can see that they're nothing particularly special. They're sort of typical 1920s, early 1930s concrete construction, reasonably advanced. These would have been high-tech factories for their day, but nothing out of the ordinary, certainly nothing that would have attracted attention beyond the town of Prato. But Nervi built a couple of dozen of these, first for Muggia and then on his own. Muggia sort of handed over some of the business to him. And Nervi got a real feel for building cheaply, building quickly, and as he would later put it, building correctly. What are the principles that make building in concrete easy? How can you kind of go with the flow, building concrete in ways that it sort of wants to be built, learning the kind of language almost of reinforced concrete. He's able to build very quickly, very cheaply, and he develops a real kind of facility for building in concrete, in particular with building concrete formwork. Now, if you know your Italian history, you know that this was a very, very difficult time to be practicing anything in Italy. Mussolini came to power in 1922, and by the end of the 1920s, the rest of the world had embargoed Italy because of its kind of excursions into Ethiopia and the human rights abuses, the war crimes that went with that. That meant that all kinds of things were embargoed, couldn't be shipped into Italy. Italy couldn't import a lot of things. For Mussolini, that was part of the plan. He had a fiscal policy called autarky, where he wanted the Italian economy to be entirely self-sufficient, to rely only on what it could produce. And in construction, this ended up being a real problem because if you look at a map of iron ore resources and of coal reserves, both crucial elements in making steel, what you find is that Italy was almost entirely left out of these. The regional geography or the regional geology of the place is that Italy is almost all limestone and has very little metallic ore and practically no native coal resources. So as you can see, they would have had to import iron ore from France and Germany, coal from Germany and England, and none of this was possible by the end of the 1920s, early 1930s. So instead, Italy had to either make do with what it had, which was not very much, or find another material. Now, for Mussolini, that was brick and stone, like the old Roman architecture. Nervi, though, disagreed with this. And he actually wrote a very brave editorial in 1938 called For Autarky, for autonomy, or for this economic autonomy, in which he said that, look, if you build the way the ancient Romans did, you are going to build buildings that are so heavy, that require so much brick, so much stone, that by the time you're done, you could have done the job much cheaper if you had used concrete, if you had taken just what little steel Italy can afford to make, used it as reinforcement, and built out of this new modern material that we have all the ingredients for. It's not a traditional Italian material, not a traditional Roman material, but it's actually much cheaper and therefore much more self-sufficient to build in this new modern material, right, concrete. Now, Nervi opens up his first contracting practice with a cousin of his, Nebbiosi, and they get the commission for the municipal stadium for Florence for a new combined football team that today is called Fiorentina. And this was a kind of fascist idea. Florence had 3 or 4 not so good football teams, and the owner of one of them decided or realized that if they could combine their forces, like good fascists, they could have a much stronger football team. And he hires Nervi and Nebbiosi to design and build this grandstand for the new team. You see what they built in 1930 on the left. This has this very famous cantilevered grandstand roof. And on the right, you see the second phase of the project, done in 1931-1932. Nervi takes up with a new contracting partner, Bartoli, in 1931. And Bartoli is a little bit more adventurous. Nervi, being a kind of a slightly restless engineer, is pleased with the kind of graceful form of the cantilever, but he also wants to explore new forms that are peculiar to concrete. And on the right, you see probably the kind of best known element of this stadium in Florence, these helical stairs. And if you think about it, they allow the stands to fill much more efficiently. On the left, you can see that the fans are all coming in at the front, and of course everyone is just going to take the front row, and people are going to have to filter through that to get back. Nervi here is solving a circulation problem. People are coming in at the back, they can drop down to the front and kind of fill the stadium from the bottom up. And to do that, he designs this double helix of a stair, too complex to actually calculate how that stair is going to stand up. And so he does something very intuitive. He makes a spiral beam that supports the stair, and then he counteracts that with a spiral beam that goes in the other direction. And he realizes he doesn't have to necessarily know what the forces in that beam are. They'll be countered by the beam going opposite direction, clockwise instead of counterclockwise, and that beam will be able to resist whatever loads that stair is putting on it. So the stadium gets a lot of press in Italy and abroad, and it makes Nervi, if not a household name, it sort of puts him and Bartoli on the map, not only as designing engineers, but also as contracting engineers. And as the 1930s go on and Italy moves closer to war with much of the rest of Europe, Nervi gets a couple of key military commissions. Now, these commissions come about because the Italian military, just like the construction industry, is facing this tremendous steel shortage. Steel is an even more important material for weaponry and for transportation, and they, having no access to it, are first of all concerned about building hangars for the Italian Air Force, which are mostly kind of these very fragile biplanes at this point. Without steel, there's no good way to build these long spans to shelter their planes, to keep them out of the rain and the wind. Nervi comes up with a kind of structural hack where he takes 3 or 4 different ideas and kind of knits them together. In this first round of hangars in 1937 outside of Orvieto, there were a pair of these, and you can see that they are a kind of arched vault, so a relatively efficient shape to begin with. That vault is arched high enough that most of the roof is going to be in compression no matter what. And then he takes that vault and he turns it into what's called a lamella structure. So these diamond-shaped patterns on the underside, these intersecting ribs. And you can think about these ribs in a couple of ways. Either they are kind of stiffening that thin shell vault above, or the way I sort of think of it is they're like the coffering in the Pantheon. They're kind of tricking the roof into thinking that it's 3 or 4 feet deep, when in fact you're able to scoop out most of the dead weight of the roof and leave this network of ribs in place that are going to channel most of the loads. So a couple of clever structural ideas there. And then combining that with, as you can see, this kind of perimeter system of buttresses that are going to take the thrust of that vault, prevent it from spreading out, and this very long triangular horizontal truss that you see on the right of the image that's going to take the thrust over the kind of open doors of the hangar and transmit those to 3 very large buttresses across the front. It's a very clever scheme, right? Combining a couple of structural ideas into one kind of unified form, and it has this very sort of pleasing pattern to it, right? The structure breaks down in a way that we recognize as kind of slightly more humanly scaled. Now, the hangars are a huge success. They come in on budget. They do a good job of protecting the planes. But Nervi is a little bit uneasy about how they actually are built and how they perform. And the reason is twofold. One is, as you can see on the right, even though he's managed to scoop out most of the dead weight from this vault, the roof is heavy enough that as it comes down to these buttresses, right, as all of those forces, all of those loads collect, as you can see, this is using an awful lot of that very, very precious and very hard to come by steel. It's using it for reinforcing, which is a little bit easier to manufacture than large steel structural elements. But as you can see, when this gets down to the base, it's pretty much a steel structure with a kind of thin coating of concrete on it. The other thing that Nervi is troubled by is the fact that because it's poured in place, it has to be monolithic. It has to be poured all at once. And Nervi essentially has to form the entire structure out of wood before he can pour it in concrete. He refers to this as building the building twice and scrapping, wasting all of that expensive timber formwork. Italy has lots of timber, but it doesn't have an enormous amount. It's been a heavily deforested peninsula since the Roman times, and timber is available but not free. And Nervi realizes that there are a couple of ways that these structures could probably be improved. He goes back to his yard in Maliana and he starts looking at ways to eliminate dead weight in the roof, and also to eliminate the timber formwork that's excessively costly. And he begins these experiments in precasting, where he's basically fabricating elements on the ground out of concrete. And because he's prefabricating them, he can use much more complicated formwork, right? He's not building formwork up in the sky. He can cast these on the ground. So as you can see, he's looking at this segment here has one arch that's all trussed up. You see that in the background. and another that's more like a Virendale, right? Thick moment connections at the edge of each arch. You can also see in the background another experiment that he made, in which he realized that you could cast larger truss elements, right, that would actually take the place of those ribs, be able to cast them on the ground, lift them into place, and in this sketch in Nervi's archives, you can see in the upper left, linking them together, gluing them together basically by taking now a wire reinforcement, not thick rebar, but thinner wire, looping them around and pouring this octagon shape of a poured-in-place concrete plug. So precasting the 4 elements that are coming into it on the diagonal, building a small octagonal box that these all frame into, pouring the concrete to kind of glue the reinforcing together, and basically finding a way to create a monolithic structure, very efficient concrete structure out of hundreds and hundreds of little pieces. And this is what that looks like. This is a close-up of that experimental rig. And you can see that instead of formwork, all he has to build to support this is scaffolding. You can use kind of scantling timber for that. And you can see between these truss elements the reinforcing wire sticking out, ready to receive the kind of octagonal plugs that will hold it all together. And this principle becomes something that sticks with Nervi his whole career. He realizes that prefabrication means that he can break the scale of the construction job down to small enough elements that first of all, a small crew of workmen can put them together on the ground. And second of all, a relatively small piece of equipment can lift those pieces into place. Nervi Bartoli is essentially an artisanal contracting firm. They don't own their own heavy equipment, they have to rent it. And therefore, if they can rent a smaller piece of equipment to lift smaller elements of construction, they can save money, right? And as you can see here, they can save, in some cases, more than 50% of the rental costs. And here you can see that this sticks with him. This is the prefabricated, precast Corso Francia, which is the viaduct that runs behind the Palazzetto and the Rome Olympic sites up north of town. So he gets a second contract with the Italian Air Force, and they at first say, we want you to just build another set just like the ones you did in Orvieto, and he says, I've got a better idea. And on the left, you see the job site for one of these at Orbitello, which he starts in 1939. That's Nervi in the suit and tie to the left, and he's standing behind a rack of precast truss elements that can be put onto this mobile scaffold that you see at the back. Simply hoist it into place. 4 or 5 guys can winch those into place, put them onto the temporary scaffold, pour the little concrete plugs, and as you see on the right, end up with a monolithic structure at the end. Because he can truss these elements up, he can save even more of the dead weight. So you can see that there's about maybe like a third of the concrete here that there was in the solid shell that he poured at Orvieto. And as you can see, he's not using any timber. He's using replaceable aluminum or steel scaffolding that can travel and that he can take from one hangar to the next and recycle it as he goes. The other really key thing that happens with these, the photo on the left is a kind of typical job site photo, right? Just someone with a Brownie camera documenting what's going on. But as this round of hangars gets completed, Nervi begins to look at it and he realizes that there's something here that's actually quite beautiful. He's not intending for it to be a work of architecture, but he goes and he hires Studio Vasari, Rome's kind of premier architectural photographer, and has them document these hangars as they're nearing completion before a kind of lightweight asphalt shingle roof goes on. And I think that what this represents is Nervi realizing that the engineering and the construction and the fabrication have all gotten so honed, right, so distilled, so kind of boiled down to their bare essence, that it's almost inevitable that what comes out of that is something beautiful, right? And I think of this as him kind of almost backing into architecture from engineering, right? Creating engineering that's so rigorous, so clear, so clearly conceived that it actually reads as something visually quite beautiful, right? The span combined with the kind of human scale pattern gives us something that goes beyond simple engineering. And just sort of to prove the point, right? There are very few drawings of what these hangars would actually look like in the archives. What you find instead when you go in there is lots of beautiful graphic statics drawings that you see on the left, calculating the loads in each of these members. On the upper right, an awful lot of drawings about scaffolding, right? Exactly how much metal does Nervi need for these recyclable scaffolds. And then on the lower right, shop drawings showing how each of these truss elements are actually made. Very few kind of perspectives, a lot of plans to show kind of where things lay out, but most of it is about the performance and about the process, about the way the statics are going to work and the way the project is going to break down into these kind of human scale elements, right, where a handful of workers can move them around the site, can raise them into place, and in doing so save the dead weight of those earlier shell roofs. Now, there's one more military experiment that Nervi's commissioned to do in the 1940s, in the midst of the war. The Italian Navy, as you can appreciate, was quite desperate, right? Because without steel, they can't build the destroyers and battleships that they need. And so they go to Nervi and say, we wonder if there's any possibility that you could build ships out of concrete. And Nervi revives a French technique called ferro cement that takes essentially kind of metal mesh screens, almost like window screens, but slightly coarser grain, bends those screens into the forms of ship hulls, and then literally just trowels lightweight, aggregate-free concrete into those. And when that concrete cures around the screens, what you get is a material that's kind of a hybrid, right? Somewhere between steel in terms of its ductility and concrete in terms of its toughness. And Nervi builds 4 of these. You can see on the left, there are a handful of steel rebars that form the basic cage, layers of screen on top of those. Then you see the guys on the right, largely unskilled laborers just troweling this lightweight concrete into the resulting mesh. Nervi is given a shipyard that has no electricity, no hoisting equipment. He literally builds these ships by hand. And the 4 hulls that he builds are, they work fine. The Italian Navy, though, is kind of on the run by 1943. They never actually go into combat. But Nervi realizes that he has something here that can kind of hack his prefabrication strategies even further. And again, later he says, look, prefabrication is one thing, but you're still building with solid pieces of reinforced concrete. And if you can take this technique, ferrocemento, and apply prefabrication to it, you can create elements that instead of being, say, 3 inches thick, right, an inch for the rebar, and then 1 inch of cover on all sides, you can actually reduce that in half, right, to about 1.5 inches, and thus take out half the weight of any prefabricated element. So weight is his constant concern, not necessarily just in the finished product, but in the kind of lifting of individual pieces. And here on the right, the Stadio Flaminio, the large soccer stadium that he built for the Rome Olympics, you can see these 2 very, very lightweight, again, rented cranes, lifting one of these roof pieces into place. Here, the Stadio roof 3 or 4 years ago. You can see that it's held up reasonably well and creates this very, very light, kind of graceful flying cantilever over the grandstand. So Nervi, by the end of the war, has this library of structural techniques and some considerable success not only in structural engineering, but also in prefabrication, and especially in this kind of hacked prefabrication that allows him to build these very, very lightweight roof sections. So after the war, in 1947, he gets this kind of insane commission for a new exposition hall for the city of Turin. Turin has always been Italy's Detroit, the center of the automotive industry. And Fiat, the largest auto manufacturer in Italy, at the end of the war convinces the city to host the International Automobile Exposition in 1949. And the issue with this is that because Turin is an industrial city, it's been bombed basically to oblivion during the war. And so Nervi has to build essentially from scratch an exposition hall on the footprint of the old hall. And to do this, he's given about 9 months of construction time. He's the only contractor in Italy that is able to meet the criteria. And the way he's going to do this is he's basically going to take the experience of the hangars, the experience of the shipyard, and combine them together. While one crew is pouring all the foundations and getting all of the substructure ready, Nervi is going to have a brigade of these unskilled laborers who are just constantly sort of following this almost algorithmic process of taking metal mesh, bending it over a clay mold, taking the resulting shape, troweling lightweight concrete onto it, and just letting it cure, and doing this over and over and over again while the excavations are going on site, essentially telescoping the construction process. On the left, you see it's from a different project, but similar process. That's a metal cage that they're lifting off of the clay mold. On the right, this is the actual job site yard from the Esposizione, where you can see literally hundreds of, I think of these as little ships, right? Canoes or kayaks, if you like, all about the size that 4 or 5 workers could lift into place or carry around easily, all ready to go the second the substructure reached its upper levels. Here, Nervi doesn't even rent a crane. He builds another one of these traveling scaffolds, and on it he puts a simple winch that 3 workers can use to hoist each one of these little boat hulls or canoes, however you want to think of them, lifting those into place, rotating them 90 degrees, sliding them down the scaffold until they meet the one that's just previously been placed, and essentially just gluing it together with a bit of concrete grout. When one whole arch of these is in place, they pour a rib at the bottom and top of each one, and they've hacked together a double hinged arch, a folded plate, ferro cement, and a prefabrication. And as you can see, also Nervi carves out windows in these elements to reduce dead weight around what will be the neutral axis in a 2-hinged arch. So there's about 6 or 7 things going on here all at once. Nervi builds the thing on time, on budget, and when it opens up, just like with the hangars, it's hailed not just as a work of engineering, but as a work of architecture. And I think the reason for this is that the kind of scale of the construction, the human scale of the construction, is imprinted on this incredibly vast span. And it reads not as a work of kind of cold technological engineering, but one that actually has some human scale to it. The auto show is a big success, and Nervi is hailed not only for this part, but also for this apse that you see on the right of the image. One of the provisions of the competition was that they wanted this kind of ceremonial space where they could give out the kind of top prizes. And as you see on the right, that is a half dome. And a half dome, it turns out, is a terrible shape structurally, right? Because the corners of it just want to flatten out. And Nervi solves this in part by building this brim around the outside, kind of a horizontal collar beam that's able to hold on to the corners of the half dome. But he also uses the same prefabrication technique, the same ferrocemento technique, now to build essentially the coffers that he's learned to use from the first round of hangars. And you can see on the left, again, here's the process where they're building now these ferrocement pans. On the right, you can see the pans tiling the curved roof of that half dome. And what's going to happen is they're going to pour concrete onto the kind of tops of the pans. Each one of the little brims down at the bottom is going to join with its neighbor to form a void that will make one of those ribs on the bottom. And the result is that you get this coffered ceiling. Again, very much like the Pantheon in Rome, where you have essentially a very, very thick dome, but without most of the dead weight, right? You're tricking this thin shell dome into thinking that it's much thicker. And those ribs all kind of carry the weight of the dome. They flow down, that all flows down onto this ring beam that you see around the edge. Again, a very kind of pragmatic approach, but one that clearly has a kind of architectural effect at the end of the day. Now, Nervi uses this process, right? Uses ferrocement not only to build roof forms, but also to build formwork. And maybe most famously, the Manifattura Tabacchi in Bologna, where he builds these kind of formwork machines that just kind of like an assembly line go down the long floors of the warehouse, kind of stamping out concrete slabs above them. You see a handful of these machines on the right. Here's what we imagine they would have looked like kind of in place. They can drop them down, move them along to the next bay. And even though no one was ever supposed to kind of see the interior, right? This is just a warehouse. He's thoughtful enough to kind of taper the pans in ways that respond to the way that the shear forces collect along those joists, and create something, again, that's kind of unintentionally fairly beautiful, right? A building that unfortunately has seen a lack of maintenance over the last 20 or 30 years, so it's not in great shape. But you can see that there is a kind of architectural effect with the detail at the edges of the pans and the repetitive structure kind of marching down assembly line-like that breaks the scale of this massive building down into something a little bit more human. And maybe even more famously, he uses this technique on this wool mill outside of Rome on the Viale Prenestina. It's now a Decathlon sporting goods store if you want to go see it. On the right, you can see these ferrocement pans now shaped to reflect the collection of isostatic stresses within the slab and funneling those into the columns. This is the beauty of ferrocement, is that because it's such a kind of molded process, because it uses jigs to make things over and over again, there's no limit to what sort of shapes you can make with them. And this is the technique that Nervi kind of perfects with the Palazzetto dello Sport. He uses these ferrocement pans, again, fabricated in sequence while the foundations are being dug for the dome. You can see here a crew of 5 guys trucking one of these pans over to the site. A crane that pops out of the center of the dome that you see on the right. Nervi rented it for exactly 30 days, and they were able to assemble something like 1,600 of these pans around the surface of the dome. You can see there's kind of rebar laying around. They're going to put those in the channels that are formed between the pans. Those will create the very characteristic ribs that you see on the underside of the dome. The whole dome is kind of picked up by these poured in place buttresses that go around the outside. So you have this paradoxical effect of the dome actually resting on top of this band of glass around the edge. And it's called inevitably by American critics, especially a concrete pantheon. And Nervi's response is, first of all, the pantheon itself is made of concrete. So that's a little ridiculous. But secondly, he's done it one better, right? Not only is the dome here, he claims eggshell thin. Okay, if you discount the ribs, it's eggshell thin, proportionally anyway, just a couple of inches. But he says, look, in the Roman Pantheon, the light comes through the oculus at the top. Here, in the 20th century Pantheon, we can actually make the roof so lightweight that the light comes in from underneath. And this gives the roof this kind of lightweight quality. It gets compared to a spider web or a sunflower, all of these kind of organic metaphors, but all of them talking about just how light Nervi is able to make a concrete seam. The real beauty of this from a construction point of view is that Nervi built a dome first, and then they came in and excavated the bowl of the arena so that they could pour all of the seating and do all of the work inside, even in inclement weather. Right? So the dome is actually not only a dome for the finished product, but it's also the kind of protector for most of the construction that goes on. This gets built as a demonstration project. Italy has to prove to the International Olympic Committee that they are in fact capable of building Olympic arenas. This is the one that sort of gets them the games. Nervi gets a handful of commissions for the actual event, including the Stadio Flaminia, the Corso Francia, and the reinforced concrete dome that beats the palazzetto for record span, the Palazzo dello Sport, the large Palace of Sport. And this to me is fascinating because it takes the same kind of ferrocement folded plate of the Turin exhibition hall, and instead of extruding it, it wraps it around a rotational grid. So you can see the deep folds of the dome. Those are all, again, ferrocement boat hulls, or wave ashlars is what Nervi calls them. They're sitting on these precast fans that then go into the ring of the upper seating, and that's the thing that restrains them, that prevents the dome from kind of spreading out. Underneath that seating tier, Nervi sort of can't help himself. He's throwing every trick that he has in there, and so you get these ferrocement pans that form the underside of the seating, right? Nervi, I think here is kind of showing off a little bit. This building, even though it's much bigger, has never quite gotten the love that the Palazzo has gotten. It's a little bit less of a clear structural solution, but nevertheless, it became iconic. The 1960 Games were the first Olympics to be televised worldwide via satellite. And so when America tuned in to see Cassius Clay win the gold medal in boxing, later to become Muhammad Ali, of course, they saw him do it under Nervi's dome. And the buildings themselves really became icons. They show up in all sorts of weird places. They become symbols for Italy's kind of resurgence, the so-called Italian miracle. The 1960 Olympics are the kind of highlight of this, right? A country that was basically devastated by World War II, 15 years later, has come back and is producing buildings that are as high-tech and advanced engineering as you can imagine. And so they show up here in Vogue magazine, right? This is inside the Palazzo in the concourse. I tell students, everyone dreams of being on the cover of Architectural Record, but, Nervi actually shows up in Vogue, right, which I think is taking it an extra mile. And his buildings show up in all of these Italian films, right? Italy is seen as one of the great cinematic nations of the post-war era, and Nervi buildings show up everywhere. So here in the Antonioni film L'Eclisse, it serves as a kind of backdrop for the long walks that the lead character takes, trying to sort of figure out what she wants to do with her life. And the dome there clearly standing for this kind of new, modern, technological society. As alienating as it may be, it's also quite an achievement. And the Olympics really turn Nervi from a kind of regional engineer who's able to take advantage of the kind of particular material economy and labor economy of Italy, and it turns him into a celebrity engineer, someone who becomes a consultant on jobs ranging from Australia Square in Sydney, with Harry Seidler on the left, to the Americas. So here in the middle, St. Mary's Cathedral in San Francisco, which he does with Pietro Belluschi, finished in 1972, and the hockey arena, one of two sports buildings that Nervi does at Dartmouth College in 1972. The second one, the first one, an indoor track, is done in the 1960s. So Nervi also is thought of often as a kind of engineer philosopher, and after the Rome Olympics, he's asked by Harvard to give the Charles Eliot Noyes lectures in poetry, which is an odd thing for a structural engineer, to be sure, but Nervi delivers this series of lectures that is later republished as the book Aesthetics and Technology in Building. And he really lays out a philosophy that I think rings really true and reflects very well the process that those of us who have worked in firms or done projects where engineering has played a really important role, not just in the performance of the building, but also in aesthetics. This is the way that it does seem to work. Nervi says that the objective data of the problem, right, the statics, the technology, which I read as the structural performance, and technology I think of as the materials, right, how you actually put these things together. So those suggest solutions and forms, right? There's a kind of palette of possibilities. But it's the designer's aesthetic sensitivity, right, the designer's fluency in the technology and statics, right? The designer has to understand the intrinsic beauty and validity that's being offered to them. Welcomes the suggestion, models it, emphasizes it, proportions it in a personal manner, which constitutes the artistic element in architecture. So technology and statics, right? Structure and construction. And then this idea that it's up to us in the end, right? The human beings who are actually holding the pencil to think about how best to kind of coax that into beauty, right? How to phrase that, how to punctuate it, how to pattern it. Nervi's kind of aesthetic decisions come only at the very, very end of a long, rigorous engineering process, a long, rigorous process about thinking about the construction. But those aesthetic choices do come, and they come in ways where Nervi is trying, I think, to show us what he knows, right? The intrinsic validity, intrinsic beauty of all of these principles. And that, I think, even if we don't kind of, build in the same way, even if we have a wide variety of other tools to use, those, I think, are the lessons that stick with us today from Nervi's career. So just as a quick plug, the 2017 book, which looks in detail at the way that Nervi's structures are broken down into these kind of bite-sized construction problems and how those get added together to create these very, very large but also very beautiful buildings. And then a couple of years ago, the Nervi Family Foundation, along with colleagues at the University of Turin, we were very lucky to be able to put out a new critical edition of Aesthetics and Technology in Buildings. So the words of Nervi, along with framing essays by scholars and also the MIT student who actually translated Nervi's lectures from Italian into English for the Harvard audience. Those, I think, are both books that show how relevant Nervi is today. I think that the takeaway for me also is that this to Nervi was all hard but joyous work, and that rigor, that discipline, that I think may have come from this very rigorous but also very broad-minded education of his, stuck with him his whole career. And here he is in that office on the Lungo Tevere in the 1960s, hunched over the drawing board, right? A drawing board just like everyone else is in the office. Ashtray in the foreground, which I think is a sign of the times. But look what's over his left shoulder, right? Even late in his career, it's that image of Studio Vasari, of the hangars at Orbitello, the hangars that were so rigorously engineered as to become architectural.